So how large is your lab? I guess together, because you both are doing machine learning.
So yeah, I currently have 2 students, 1 postdoc and some masters and undergrad students. But in the fall, I'll have 4 students. I think Tyler has been here longer than I am, so yeah, his lab is a little bit more established than mine.
Yeah, but some ups and downs of graduate students joining. So it'll be 3 PhD this coming fall.
Oh, okay. And are there more machine learning faculty, or it's just 2?
Yeah, we have a few, and so I don't know if you know it, but Vanderbilt has this destination CS and destination Vanderbilt. We are hiring a lot of new faculty members, and so we're growing in the area of machine learning in general. Like there is a specific interest on medical imaging, so application of machine learning in healthcare, but like we have hired somewhere like core machine learning faculty members as well. So it's certainly growing. Yeah, but currently I think
Nice.
like I can name like 4 or 5 core machine learning faculty members.
Nice.
Okay, so it's 12:18. Let's start. Hello, everyone. Thank you for joining us for the machine learning launch seminar today. Today we are lucky to host Hossein Mobahi from Google Research. Hossein is currently a senior research scientist at Google, and his research interests revolve around the interplay between optimization and generalization in deep neural network. Before joining Google in 2016, Hossein was a postdoctoral researcher at CSAIL at MIT. And before that, he was a PhD student in the computer science department at the University of Illinois at Urbana-Champaign, UIUC. With that, Hossein, the stage is yours. We look forward to your talk.
Thank you so much. Thanks, everyone, for coming to this talk. I apologize about the last time that we tried to have this talk. It didn't work out. I'm sorry about that. And also, there's a glitch with my camera today. So you don't have my camera, but hopefully the voice is clear and the slides are good. So yeah, without waiting further, let me switch to slides. Okay, full screen. Okay. And by the way, I'm now doing full screen, so I don't see your faces. If there are questions, feel free to stop me. I don't see your
Sounds good.
text or face.
Right. If there are any questions, please post it in the chat, and I can interrupt Hossein and ask the question. Yep.
All right. Okay. Thank you. Yeah. As Sohail said, today I'll be talking about sharpness aware minimization, so-called SAM, about the current state and some future directions, open problems for researchers to work on. This is joint work with Pierre Faure, Ariel Kleiner, and Behnam Neshabur. So the outline of the talk is that first I'll give a quick introduction about SAM and discuss some related work and motivation, then present the algorithm, go over some empirical results, and then discuss whether it really works, in the sense that whether others have also observed gains. This means just our paper. And finally, I'll discuss some open problems and future directions, which could be useful for people looking for open problems in machine learning. Okay, so what is SAM? SAM is an optimization algorithm similar to gradient descent, but what it does on top of gradient descent is that it tries to find flat minima. And I think one reason for this, if SAM has been successful, one reason for that is that it's efficient, computation efficient, and also easy to implement. And we will see each of these addressed later in the talk, why I call it efficient, why it's easy to implement. And importantly, it improves state-of-the-art performance on some benchmarks, especially in image classification, including ImageNet and CFAR. And a lot of other gains that I'll discuss throughout the talk. But here you see a visualization of the landscape and why What I mean by seeking flat minimum. So on the left, you see the loss landscape. Of course, it's a projection because it's high dimensional. But if you run SGD on ResNet and let it converge, this is a solution that it finds. And then if you run SAM on the same architecture with the same data set, you will get a minimum that looks like the right one. So just qualitatively, visually, this is how they find their minima. And I mentioned about state of the art. So this is something that you can always check the up-to-date results from the website Papers with Code. So there, if you search for a specific data set, they will rank different techniques with the performance they have obtained. So it's kind of a unified comparison and also very up to date. So this is something that I fetched quite recently, and you can see that on both CFAR and SVHN, SAM is actually #1. So on ImageNet, it used to be the top. Now it, because ImageNet is being tackled like constantly, so it's no longer the top, but it's one of the like high performing methods there too. And as I said, it's just a few lines of code. I don't want you to focus on the algorithm here because I haven't explained a lot of the details that we need to address before getting here. The point here is that just this is what the algorithm looks like. There's no like complicated operation. It's just basic algebra and computing the gradients and things like that. And as we proposed the initial technique SAM, the sole goal was to improve generalization performance, but people adopted that and played with it and observed other interesting areas where SAM can be useful. So these were not intended in our original, when we were originally writing the paper or implementing SAM, but these are interesting observations. For example, one thing that people have observed is that if you, for example, here is like a vision transformer feature map that you can see. And if you train your architecture with SGD versus SAM and look into the feature maps, then the feature maps of SAM are the one on the right. And you see that they kind of look like more like a object. They preserve more of the object structure. The original images are on the left. While in SGD, you can barely see the trace of the object structure there. So this might be important for people who are working on interpretable machine learning, because here you can clearly see the objects and know exactly what is being picked up by the network. Another thing is the efficiency of the technique. So there's a website called Mosaic ML, and what they do is that they, like when you want to book a flight, they collect a bunch of preferences and constraints from you, like what is your computation budget, what is the data set, and so on. And then they basically search for the best suggestion, which kind of balances the cost and the performance that you desire to achieve. And SAM is actually their #1 recommendation, which gives like the perfect balance between the cost and performance that you want to achieve. And another observation, again by some other folks from University of Maryland, is on the reproducibility. So when you train the model with SGD versus SAM, you use random seeds. What they have observed is that with SGD, the performance you report is more sensitive to these different seeds that you use, while with SAM, you more or less get the same performance each time. So for reproducibility perspective, again, SAM seems to be more robust. And most recently, there has been DALI 2, which has been in the machine learning news a lot. And if you read their technical paper, you will see that they have used SAM for training their clip models. And they say that SAM not only improves the performance according to the metrics that they have, but also the representation they get for their clip using SAM is much lower dimension than when you train with SCD. So that means that your training data will be on a lower dimensional subspace when you use SAM. And this is important for them because later down the road, they need to reduce the dimensionality of their representation that they get from clip so that they can scale their algorithm, and they have more success with SAM because there's less sacrifice of fidelity against cutting the number of dimensions. Okay, so with this advertisement, let's now get to the technical part of understanding what is SAM. First, I'll introduce some notation. We denote a training set by S. It's a supervised setting, so we have pairs of input, output, X, Y. We have a neural network. Its weight is parameterized by the vector W. We also have the per data point loss, which we show by small l. It takes the training data and the current model and returns a value, the cost of like classifying according to this model, like how off the prediction is from the ground truth for this input. And using that, we can define the average loss of over our training data by simply plugging individual training points into this per data point loss and computing the average. The reason we compute this average is because it can give us an approximation to the true loss that we wish to minimize, which is if we knew the true distribution of the data, then we would want to basically compute the expected loss and then minimize that expected loss so that we have a good performance over unseen data as well. But the problem is we, of course, don't have the full distribution. We only have the training samples, and we use this average loss as a surrogate for minimizing the true loss. So we typically minimize the LS with respect to parameter W. Okay. The problem is that with neural networks and many modern machine learning models, we are in overparameterized setting, which means that the number of parameters is way larger than the number of training points that we have, which implies that on the loss landscape, there could be many different points, many different Ws that can fit our training set with nearly zero loss. But these are still different points in the sense that they behave differently over the test data. And here's one concrete example to show this. This is something that we ran. And the only thing that we are changing here to create different data points is the batch size. So this is run on CFAR10, and we train our deep model with different batch sizes each time we try this, because as I said, the model is overparameterized. We can get 100% training accuracy, and the training loss is also nearly zero. I mean, it's zero up to 2 digits that we report here. But as you see in the test accuracy column, they have very different test accuracy behavior. So this is just showing that there are indeed multiple points on the landscape which can achieve zero loss, but still they have different generalizations. Some are better than the other. And this is indicating that just going by the loss value itself is not enough to obtain models that have good generalization performance. Many of you may know this already, but just for the sake of completeness, I wanted to have this with concrete numbers. So we are on the same page. And yeah, so now we get to the SAM algorithm. So SAM is one way of preferring some global minima versus others. Global or like maybe local minima, but with very low loss values. So it tells us the following. So this is a theorem from our paper, which gives us an upper bound on the true loss. So the true loss is on the left-hand side, and the bound or the result that we have is on the right-hand side. So it tells us that if we can find a parameter W that lands at a point that's somewhat smooth, and the notion of smoothness here is defined by this like adversarial choice of perturbation epsilon. So suppose you give me some W and you say, okay, this is like your model converged to this point W. I search a small neighborhood around that W and see, okay, what is the largest value of training loss that I can get within that neighborhood? And if that is still small, then I can guarantee that my true loss is also going to be small because of this bound. There's also a second term, which I'll get to it in a second. But the first term, which is the max term, that is about this ball and the adversarial chosen perturbation. So it's basically saying if you land at a point where it's kind of flat, so if you perturb the point, the loss doesn't increase that much, then you're in good shape. The second term is some monotonic function h of its argument. So it's basically saying that you also want the norm of the weights to be small. And the exact function of h is provided in our paper, but we think that the form of h is the exact form of h is basically includes some artifacts of the proof techniques. And what matters there the most is the fact that h is monotonic. And based on that, we just suggest that you can remove h and just use identity function. So just penalize the two norm of the w, and also the SAM algorithm uses that approximation, and we will see that it works with that. So it kind of confirms that you can not worry about what is the exact function of h, just penalize the norm of w, and that does the job. Okay, so this is a generalization bound, but now let's see how we can get an algorithm out of this, because this bound is nice, but still there are some components in there that are not tractable or are expensive. So we want to see how we can arrive at an algorithm that we can deploy in practice. We already did one approximation, which was removing h and replacing it with identity function. So that reduces the algorithm to just that term to just weight decay. But there are a few other approximation we will basically use before getting to the full algorithm. Okay, but before even starting, let me show you where the sharpness come from, because we have this bound and we are now focusing on this left-hand side term. By the way, so can you confirm if you see my mouse pointer?
Yes, we can.
Okay, okay, great. Yeah, so let's first focus on this term here. What I'm going to
Hossein,
do, yes,
may I stop you and ask a question there on the previous slide? So the goal is to minimize the upper bound, right?
yes,
Okay, got it.
yes. So this is what we basically set as our goal to develop the SAM algorithm, but this is still not something that, as I said, all the terms are being tractable or at least efficient. So we will make a couple of approximation until arriving at a practical algorithm. But hopefully we are not deviating too much also from this exact form.
Got it. Thank you.
You're welcome. Okay, so what I do here is I'm just subtracting and adding the empirical loss. This doesn't change anything, right? But now this term in the bracket, I can think of this as the sharpness, right, at the point W. Because again, it's saying that if I'm at the point W, I have some loss value at that point, and then if I perturb it to obtain the maximally increase in loss, maximum increase in loss, and compute the difference, that's kind of the sensitivity of the loss within that ball, right? So it represents the sharpness measure that we are considering. So it's more intuitive to see it when you like subtract and add, because now have a better sense of this. It looks like a sensitivity criterion. And this is the usual empirical loss. So from this viewpoint, we are minimizing sharpness, which is the bracket, plus the average loss itself. So it's a combination of these two. And we have this term as well. And this is just, as I said, we're replacing this h with identity function. So this simplifies our final algorithm to minimizing the loss of SAM plus weight decay, where the loss of SAM is just this guy. So it's also defined here. It's just computing this maximal point and then trying to minimize the loss at that point. Okay. So as I said, this is not yet a practical algorithm. The first reason is that we have to compute this adversarial perturbation. It involves a maximization of the loss. And it's as hard as a minimization because we are dealing with this highly nonlinear function of neural network. So we cannot really solve this up to, like, we cannot really solve this efficiently. But what we can do is to leverage the fact that we are assuming the perturbation is within this small ball. So the norm of epsilon is going to be small. Rho is the radius of that ball. So we are assuming that rho is small. And this enables us to rely on a first order Taylor series of the loss with respect to epsilon around epsilon being 0. So if you just do this first order expansion, you get this this new approximate objective, right? And this term is just a constant with respect to epsilon. Remember, we are maximizing this whole thing with respect to epsilon. We are first trying to find this adversarial perturbation. So we can just drop this first term. It doesn't affect the argmax. And we just remain, we're left with this dot product, which is epsilon dot product with the gradient of the loss. And this is a nice problem. We have a linear objective subject to a norm constraint, and this has a closed form solution, which relates to the dual norm of whatever norm we are using here. So if we are using a p norm here to define our ball, its dual norm is denoted by q, and then you can express the closed form solution of this epsilon in this way, which again, the full detail is available in the paper. But what works most conveniently and also to our best knowledge with experiments that we did is just using the 2 norm. So it simplifies the form and also seems to work very nice in practice. If you replace p with 2 and just use the 2 norm, then this form of epsilon simplifies to gradient divided by its norm. And by the way, here you see that the epsilon, optimal epsilon is shown by epsilon hat. That's because it may not be equivalent to epsilon star because we switched to an approximation and there might be some discrepancy. That's why in the notation we're using this epsilon hat here. Okay, so we found a way to approximate this epsilon star and we call it epsilon hat. And so the objective of SAM can now be written as computing the gradient of the loss at this point where W plus epsilon star is now replaced with epsilon hat. And now suppose we want to now go and compute this gradient because eventually we want to do gradient descent on this loss of SAM, right? So when we want to compute the gradient, we have something a little bit delicate here. So the argument is W plus a function of W, right? So we will use chain rule, standard technique. So in order to compute the derivative of this guy with respect to W, we need to compute the derivative of the argument of this function with respect to W. So this is this part times the gradient of the loss evaluated at this point. So this is the second part. The gradient is first computed and then it's evaluated at this point. Okay. So this first part, which is the derivative of the argument, it has two terms. The first term is just w itself. So the derivative of w with respect to w is just identity. So if you focus on the first term, it just identity times this gradient term, which you see in red here. I'm just moving all these like things that involve the first term, showing that in red. And then this second term, though, it will involve higher order derivative, actually second order derivative, because the epsilon hat itself depends on gradient. As I said, for two norm, for example, epsilon hat, optimal epsilon hat turns out to be normalized gradient. So it's already a derivative there, and then you're taking the derivative of that derivative. So it will be a second order term. So I don't write it explicitly, I just leave it as d of epsilon hat with respect to d of w times, again, this guy. And this is shown in blue. Okay. Is any questions so far? Okay.
So far, so good.
All right. All right. So as I said, we have these two terms. The first term, the red one, is just computing the gradient of the loss evaluated at this perturbed weight point. And the second term is something that involves second order derivatives. And indeed, we can compute that because it involves a Jacobian times vector product. But still, we can cut some computation by ignoring this term. And then like in the further in the talk, I'll show the effect of having this term versus not having this term, and we'll see that it doesn't really buy us much to keep this term. So we just discard this term. It looks like most of the juice is coming from the red term, and it's also easier to compute. So we will move forward with the red term for implementing SAM. Okay, now I think we have all the ingredients together, so I can show you what the pseudocode of SAM algorithm looks like. Suppose we have a mini batch. What we do is we first compute the gradient of the loss over this mini batch. And assuming that we are using the 2 norm for defining our ball, then we will need to compute the normalized gradient, which is just this term. And then we define W add as the current iterate plus this adversarial perturbation epsilon. So that's our W add. And what we do is eventually computing the gradient of the loss of this mini batch that we named it delta at this W add. So that's the gradient that we will, that's basically the vector that we will use in order to update our parameter. So if this was just a vanilla gradient descent, instead of G here, you would have the delta, because delta is the gradient, right? But now it's going through this adversarial perturbation and modifying SGD with like this change, replacing delta with G here. And it's as simple as that. You iterate. So it's very like simple to implement. And here I have an illustrative example of what happens again in the loss landscape. Hopefully this is more clear than the pseudocode. I'll walk you through this example. Suppose your current iterate on the loss landscape is shown by this WT. Okay, and this is the gradient direction on this loss. So as you know, the gradient is perpendicular to the ISO contours of the loss. So these are the ISO contours. So the gradient has to be in this direction, right? And here we are going to the direction that decreases the loss. Sorry, this is the direction that is increasing the loss. So like hotter, warmer colors show higher loss value. In gradient descent, we negate the gradient direction. So instead of going in this direction, we go in this direction. We multiply with some learning rate and update, basically move from this point, the negated gradient direction and arrive at WT plus 1. So this is what we would do if we were doing SGD. Now with SAM, we first compute this adversarial perturbation, which, as I said, when we use L2 norm, it's just normalized gradient. So it's the opposite direction because it's not negated, right? It's actual gradient. And if we add that to WT, we basically move along this direction with this size, we arrive at this point, which we call the W add. And then we compute the gradient of the loss at this point W add. And once this is computed, this is what we use in order to update our point. So our point WT moves in this direction and by this magnitude in order to obtain WT plus 1 for SAM. Okay. Any questions so far? Okay. So let me check the time. Okay, in the interest of time, I'll skip some of the performance numbers because these can be found in the paper. I already discussed that with SAM, you can achieve state of the art on some important image classification benchmarks. So I think I can skip these. These are basically showing that in both cases of training from scratch and fine tuning, you can see gains from SAM. And let's get to the parts of the talk that maybe are more important than just numbers in the table. Okay. So we get to this part, which I call, does it really work? And by that, I mean, okay, we wrote a paper, we reported some numbers, but you know, these days there's a reproducibility crisis. So people claim that they have something that works, others try it and it doesn't work. So here by does it really work? I'm referring to the fact that how others tried it and what they saw when they used SAM. So one of the most interesting papers, in my opinion, is this one. So what they do is that they train two different architectures, VIT and MLP mixer, with SAM and with SGD. And what they find is that with SAM, they see a substantial gain in absolute test accuracy, not relative, absolute gain. And yeah, here you can see that with I guess yeah, with MLP mixer they get 11% improvement. With VIT they get more than 5% improvement. So these are significant numbers, and they also try to justify that by seeing what is the loss landscape and showing that, okay, like with VIT and mixer, this is what you would find with SGD. So it's kind of a sharp minimum. But if you use SAM, then with VIT and mixer, these are the things that you find. And one side observation from that paper was also that they see less gain with SAM on ResNet, and they believe, they basically conjecture that's because ResNet loss landscape is already kind of smooth and flat because of this skip connections, which makes the loss more well behaved. So there is little left for SAM to basically help because the loss landscape is already smooth. But these numbers were quite striking, and this paper is not that old. It's actually from 20, yeah, from this year.
Hossein, I have a naive question, if you don't mind, on the previous slide, right? These plots are great, right? I'm just wondering, like these plots are showing two parameters, right? Loss landscape over two parameters. How do we choose these two parameters? Right, we have millions of parameters in like ResNet, right? Like 11 million, for example, or like so. Yeah. What are these two axes? The two dimensions that we are choosing. What are those dimensions?
Yeah, very good question. So actually there is a standard tool, kind of standard tool now that people use. So the original paper was from University of Maryland, from Tom Goldstein's group.
Yeah.
Yeah, where they had this visualization of lost landscapes, and they also published their code, which they use. And now people are using it as kind of standard tool for visualizing the lost landscape. They have, various criteria in order to pick these two important directions for projections. So I don't recall all the details, like what criteria they use. But we are building on that, like the landscape we showed, like I showed in the first slide, that's also using the same tool, and what this paper is also using same tool.
Okay,
So
got it. Thank you. Yep.
okay, so that was about like numbers, but what about domains? So this was still with image classification. Does it work in other domains? And again, the answer is positive. Papers are emerging. The first one, which I show on the top left, this is our own paper where we use SAM for NLP, but there has been a lot of other areas explored by other people, which some of them are represented in this slide. And there are also a lot of follow-up works. People are trying to extend the vanilla SAM, and you can see there are a lot of variants of SAM. And this is interesting because all of this has happened over the past year. The SAM itself is not that old, but the community is actively working on, improving SAM. So I think these are all good signs that SAM works. So that was the title of this section, that okay, if it didn't, then there wasn't this much of engagement from the community. Another sign of whether it's work or not is seeing, okay, how much it's being like how much people spent effort on coding it up and making it publicly available. So as of now, there are more than 11 public implementation of SAM, and in PyTorch, in JAX, and TensorFlow, and yeah, some of them are actually quite popular here. So with popularity measured by the stars on GitHub. All right, so we are getting to the final part of the talk, which is the open problems and future directions. Sohail, is the talk exactly 1 hour? So do
Yes,
we
we
finish?
have until
Okay.
1:15. It would be great if like we have 5 minutes for question, but yeah.
Yeah, I think we have enough time. Yeah, just check.
Okay, perfect.
Okay. Okay, so open problems. One of the, I think, obvious open problems is, as you saw, we were making a lot of approximations from like the original theoretical bound all the way to get the practical algorithm. And each of these approximations, it seems that it's working. We have like done some experiments to make sure that we are not losing too much by replacing the exact form with the approximation. But the reason why this approximation is good itself is not well understood. Why, for this setup, these approximations happen to give you, still good performance, why you're not losing too much. That itself is like important open problems. So one of the first approximations that we used was when we linearize this inner optimization, the maximization step. When we wanted to find this adversarial perturbation, basically what we did was we replaced the original difficult maximization with just a linearized version, and just do one. It's equivalent to just doing one step of gradient descent, because gradient descent also just looks at the linear approximation of the loss, which is computed by the gradient. So one natural question is, what happens if you iterate for a few more iterations rather than just doing maximization step for just one update of parameters with gradient descent? What if you do a couple of gradient descents? And also, because you have this norm constraint, you need to make sure that you never exit this ball. So if you iterate for like longer and you leave the ball, you have to project your solution back onto the ball to make sure that you meet the requirement of that ball constraint. So we did something limited here, just increasing the number of optimization steps to 5 steps instead of 1, and seeing how things change if we do that. So on the left, you see what's happening with CFAR 10. This is the updates, and this is the value of the sharpness. So if you remember, we define sharpness as this max minus the loss value. So it's kind of showing the sensitivity value. And these different colors are showing the number of steps you use in order to do gradient ascent on the maximization problem. So one step is vanilla SAM, the default SAM. And because this is the sharpness value, the larger is the better, because it means that, okay, we indeed succeed to find like a point of higher loss, because the inner optimization is trying to find a point of higher loss. So here the larger is better. And you can see that with more iterations, we indeed can achieve larger sharpness. So the difference is small at the beginning, but it increases toward the end. And similar trend with CFAR 100. But how much does this buy in terms of improving test accuracy? It turns out it's not too much, a little, but not too much. So here's showing the test accuracy when we use different number of gradient steps. So as you can see here, with increasing the number of steps, the error can decrease a little bit. Actually, here at the 5th iteration, it again goes back up. But if you want to consider like 2 or 3, we can decrease the error a little bit, but it's not like too much. So maybe it's not worth doing, making the algorithm 5 times, 3 times more expensive for just this much. So eventually it kind of gives us the confidence that by just doing one iteration, we can still do good. And similar observation with CFAR 100. So this is the test error rate. We can slightly decrease that by running it for longer, but again, it's not too much. So this is, again, just giving us peace of mind that we are not like doing terrible by making this approximation. But why first order is enough, that itself is, like, as I said, open problem. So what is the property of the loss landscape and the dynamics of SAM and all that enables us to do this with only one gradient descent? Another aspect of SAM which is not explained by the theory is something that we call M sharpness. So when we first implemented SAM, we wanted to leverage parallel computing. So if we have a batch, we wanted to distribute this batch to different workers. Each of those compute their own gradients, and then they would send that the gradient back to the center, and we would aggregate those gradients. So what happens is that in each of these workers, the WAD is computed independent of others. So each of them computes, because each of them only receives a subset of the mini batch, right? And it can only compute WAD up to that mini batch that it can see. So each of these workers computes its own WAD. And then when we aggregate these to compute the final loss, something we observed was that doing this distributed computing actually can further improve the generalization performance of the model. So saying that instead of like taking the full batch and computing the only one WAD for that batch, if you do multiple mini batches, compute the WAD for each of them separately, and then aggregate the result, then you get a better generalization performance. So this plot is showing the error rate versus the number of samples per workers. And you can see that with, like, as we increase the number of the sample size, like as we go toward this cyan, the error rate can increase. And the best error rates come from the colors that are smaller than 256. But exactly why this is the case, like how like having these splits, computing the W alpha across them and aggregating them can improve generalization. This is not explained by Airbound. Actually, Airbound doesn't even assume that you are splitting. It looks like there is an ICML paper this year that says, I think, towards understanding sharpness aware minimization or something like that, and they have some explanation about why this works. So I'm looking forward to reading that paper. Okay, another approximation came when we said, okay, we ignore the blue term. If you remember, we had a red term and a blue term. The red term was only the first order derivatives. The blue term involved second order derivatives. And we said that for simplicity, we dropped that because we see it doesn't really like bias much. So here is again some limited analysis, empirical analysis to have some peace of mind on that. So this is showing wide ResNet on CFAR 10. On the vertical axis, you see the error rate, and yeah, I think that the plot itself is like explaining. So the test error are the dotted points, and the solid lines are the training error. And the second, when you keep the blue term, the plot is also blue. When you only work with the red term, then it's shown with orange. So as you can see, the performance, especially at the beginning and at the end, doesn't change that much. Somewhere in the middle, there's a gap between these two, but near the end, those kind of merge. So it's showing that when you like obtain a converged model at that point, whether you had a model trained with the full second order term or whether you eliminated that, you achieve the same error rate here. And this is, by the way, test, because these are dotted. Same with the training. So near the end, when you converge, it doesn't really make a difference which one you picked. So again, peace of mind, but why this second order term is not important? That's something that we don't know. And understanding and explaining why this is the case is something that not only justifies SAM, but I think the insights could be uh, uh, like very valuable.
Hossein, I have a fast question here. So it's surprising that the second order is actually slightly worse during the training, right? Like that's
Yes,
counterintuitive, isn't it?
it is counterintuitive, but I think with Taylor expansion, this happens a lot because Taylor expansion is a local approximation, right? And the error of that local approximation grows rapidly as you move away from that point that you're using Taylor series. And how fast it grows is depending on like what what is like the error rate that you cut off. So for example, if I stop at so basically if you look at the Taylor remainder theorem, then you have the error is composed of two terms. One is like what is the largest value that the higher order derivatives can take. The other is the distance of your point from the center, and that's raised to a power, and that power is the order of the cutoff. So if I cut off my, I don't know, my Taylor series at order 3, then this uh, x minus x0 term will be raised to power 3. If I cut off at 2, it will be raised to power 2. So this means that if you go farther from your linearization point, or whatever, like whatever order you use, um, the error can grow very fast if you use higher order Taylor expansion, right? So here, if it's like we are comparing linear versus quadratic, so the cutoff will be exponent 2 and exponent 3, right? So for this for the second order approximation, we have x minus x0 raised to power 3, which means if you are close to the x0, then okay, very good. Actually, it's even smaller than raising to power 2. But as soon as you go like a little bit far from x0, then this gets amplified much more than raising to power 2. So do you see my argument?
Yeah, I think we can talk about it offline. Yeah, but for the sake of time, let's continue, and maybe we can come back to it at the end of the seminar.
Okay, let's see if
Thank you.
I
Thank
have.
you, Dr.
Yeah, you're welcome. I actually kind of reached the end of the talk, so we can quickly go back to that. But also, like some of these examples, observations that I mentioned earlier in the talk, observed by others, are also open problems again. So for example, here with this figure, we had VIT and MLP mixer working very well with SAM. So what can we say about architectures in general, how they interact with SAM, what aspect of the architecture makes it fit better for SAM, and whether we can use that knowledge to maybe even design new architectures that are more compatible with SAM, and we get even more performance gain from that. Why, when we train with SAM versus SGD, the resulted feature maps are more object-like, why it's like easier for us to understand what objects is in there. Why with SAM we get more reproducibility. Why with SAM we get the lower dimensional representation. So these are all open questions that are interesting if anybody wants to tackle. And the list of open questions can go on forever. So whether we can have a schedule for this radius row, because we have a schedule for learning rate, right? So as like we kind of like if we have a schedule for learning rate, then should we have a schedule for row? And if we should, then whether it should be synced with the learning rate or not. And another open question is about adversarial sharpness, which SAM was based on. The reason that we built SAM on adversarial notion of sharpness is because from our previous paper, fantastic generalization measures and where to find them. Well, that's before SAM. We were just doing empirical investigation of different notions that people think can have a role in generalization. So the size of mini batches, sharpness, and a lot of things. And there, when we were doing when we were using sharpness, we considered two variants. We considered the adversarial one, which is used in SAM. We also considered the average one. So the average one is, instead of like maximizing, you just replace that with the expectation. So you are computing the average value of the sharpness within that ball. And what we observed in that fantastic generalization papers was that with adversarial one, we have a adversarial one has a much better correlation with generalization than the average one. So the average one was not that much predictive of generalization performance. And that was our motivation to build SAM on top of this adversarial one. But again, why adversarial sharpness is so good for improving generalization and average one is not, that is not well understood. So these are all, I think, open questions that we can think about. And now I think this is the end of the talk. So thanks everybody. If there are questions, I think we have a few minutes for question. If no question, we can get back to Sohail's question.
First, let's thank our speaker for this wonderful talk. It was fantastic, Hossein. Congratulations on the approach and congratulations on the fantastic talk. Right? Let's thank our speaker.
Thank you.
So questions.
Hi, Hossein.
Hi.
Nice talk. Can I first make sure I understand it correctly? So the generalizability of SAM basically comes from it's able to find the local minimum that is more sharp. Is that correct?
Not sharp. It's
Oh,
flat.
more flat, more flat.
Yeah.
Okay, so why would a more flat local minima is better for generalization?
Okay, so if you want intuition or you want a theorem. So if you want a theorem, then the like the generalization bound that I showed, it's actually part of our paper. So if you go there, you see a full proof about it. But if you just want an intuition, like in a minute, I think the easy one would be to think about a loss landscape. Okay, so think about a loss landscape where you have a sharp minimum and a flat minimum, and suppose that because you're only like building this loss landscape based on the training set, right? You don't have the test set, so it's going to be different from the loss landscape that you build when you have the full distribution, right? So let's suppose that the full distribution maybe shifts the location of this minimum by a little bit. Just let's model that, model the difference that way, right? So now you can see that if you are finding a sharp minimum and the location of that minimum is shifted a little bit, you can easily fall into the basin of attraction of another minimum, right? While if your minima are flat, even if you shift it a little bit, you still are within the basin of attraction of that minimum. So when I switch my loss landscape from training to test, where again I modeled that by just shifting the location of the critical point, so I'm still within that basin of attraction. And also because the loss is flat, more importantly, because the loss is flat, the value of the loss is not going to change too much between these two points. So again, the point is that even though I'm shifting the location of the critical point a little bit, when the loss is flat, this shift doesn't cause too much difference in terms of the value of the loss, right? And here the 2 points that I'm talking about are from the training and the true distribution. So if I shift the location of a minimum a little bit, because the loss is flat, the vertical axis, which is the expected error or accuracy, whatever, that's not going to change too much, right?
That makes sense. Thank you.
Yeah. But if you want a more rigorous proof, it's in the paper.
Gotcha. Thanks.
Thank you.
Hi, Professor. Thank you for your brilliant talk, and it's really great. You provide an efficient and effective optimization with good generalization. So I have a question related to the interpretation. So you mentioned that SAM will bring benefits in providing good interpretation, and you also state in the end that it's still an open question why it works. I have a guess for why it works, and I want to listen to your opinions. So the guess is, since SAM wants to avoid the sharpness and it will prefer more smooth solution. So with more smooth grades, we might avoid paying too much attention on like certain pixels. So in the original optimization, like SGD, we might focus on some certain pixels, but in SAM, we focus more in a larger region. So it will show in the heat map that might be more related to objectives human can understand.
Yeah, I think that's the right intuition. I also have that intuition. I think the gap is making this rigorous. So if you want to write a paper, you need to do more. But that's a good intuition to begin with. But then you need to explain, okay, why, like with SGD, you may, for example, lock onto these very local features from the image, but with SAM, it looks at more global pattern. So that still need to be shown, but the intuition is I agree that that's something that also think that's the reason.
Okay, as a follow-up question, so I think we have a trade-off term to control how much constraints we have on the sharpness. So do you have like every test, if we change the constraints, for example, if we soft the constraints, will we observe a change on the heat map?
So that one, I don't know. That is done by, that's like another paper, so it's not authored by me. And I think they just ran their experiments with the default parameter value that our paper suggested. I don't think they tried different numbers and see how that affects the heat map.
Okay, thank you.
Thank you.
So there's another question in the chat, Brian. So Brian is asking, he's wondering if the experiments comparing SAM and SGD results in the table that you showed are based on the same amount of training time. So the same wall clock, essentially. Are the wall clocks the same in those two problems? In the sense that SAM computes gradients twice, but did it run twice as much as the SGD? Are the epochs fixed, or is the wall clock time fixed?
I think epochs is fixed. We have a max iteration, so it stops at that point. And it's true that yes, each update of SAM is more expensive than SGD because you need to compute the gradient twice, right? One for computing this WAD that uses a gradient, and then using that to update your W, like do a descent direction. So that's the second one. But one thing I should say that actually it was in the open problem, but because we were almost out of time, I didn't emphasize too much of it. So that's about efficiency. So it's one of the open problems, that how we can make SAM more efficient, because currently it doubles the gradient computation. The time doesn't double exactly. The number of gradient computation doubles, but the time doesn't double exactly. So it's just some overhead. But still, it's good to make it more efficient. So some tricks that people have used has been to like compute the WAD based on a smaller subset of your mini batch and then apply it to your entire mini batch. So you don't, basically the WAD is like faster gradient computation than the second gradient, which applies to the mini batch. So that's something that people have proposed. And I think recently also there was a paper called I think SAM. They were also like investigating around efficiency, how to they were proposing to switch back and forth between SAM and SGD throughout the training, and then they had some findings about okay, where to do this switch and how many times. So yeah, it's one of the open problems, and I'm trying to in the meantime find that paper to give you the correct title. Yes, it is SS-SAM. If you just put that in quotation mark and search in Google, you will find that. So they have some ideas how to improve, but this is still a big open problem again.
Great, thank you. I have one more question, Hossein. And sorry, we are running over time. Is that okay with you that we are running a little over time?
Yeah, I'm okay with that.
Okay,
I don't know if
perfect.
you're okay.
Yes, so we're fine. I think the questions are mind tickling. So a quick question is about the batch size, right? So in SGD, we know that smaller batch size leads to flatter loss landscape, right? Like, so essentially when you have SGD, which is small batch size, your optimizer can escape these very sharp local optimas and end up in the flatter areas. And I think you had that in one of your tables showing that with batch size 1, you get the most generalizability.
Right.
Right. So, but
Yeah.
like, what is the effect of batch size on SAM? So like how does batch size, how is batch size affecting SAM?
Yeah. So again, batch size has effect on SAM. So I had the one slide on that. So it wasn't quite the batch size. So okay, what happens is that we take the conventional mini batch and then create a mini batch out of it. So each of like, so we take a mini batch, we partition that into smaller subsets, and then send that to different workers. So this way, like the size of this mini batches is again another, I think, parameter that's kind of related to the question that you're asking. And as I showed in one of the graphs, when this number is gets large, we lose a little bit performance from SAM. I mean, still SAM, but the best performance of SAM comes when this number is not that large. So if we work with 256, for example, you get the error rate of this cyan curve, which is higher than the blue or the magenta curves, which are with like smaller number of samples per mini batch.
Right, but these are in the distributed computation setting, right? Like that you have mini batch, right? Like
Yes.
like what if we just have like one worker and change the batch size for the one worker?
Yeah, that's something that yeah, I don't know because we didn't run anything like that. Like in all
Okay.
these experiments, we had to distribute it across multiple workers.
Right.
So I don't know the answer to one worker and then changing the mini batch size.
Any more questions?
So I guess one question I would have is, so related to robustness on noisy data, that I saw in the paper some experiments there. And I was wondering if you have done any follow-up work on that, or if you're aware of others as compared to these like mix-up based methods.
I cannot think of any method that kind of gets deeper into this with SAM. I have seen papers that have confirmed this, like they have confirmed that yes, if you have noisy labels, then it really goes better with SAM than SGD. So that one I have seen, but in terms of like improving our understanding or algorithm, no, I'm not aware of any.
Okay, yeah, because intuitively it makes sense, and then just thinking of yeah, some dedicated efforts in this direction would be pretty interesting.
Yeah, exactly. Because intuitively you have some robustness, right? Although it's in the weight space, but why that translates into, labels, that connection can be made solid, and I don't think it's been made. So yeah, it's something that needs to be done.
All right. Interesting. Thanks.
Yeah, this last sentence that you said is really interesting, right? Like the robustness with respect to the weights, right? The flatness of loss landscape. But then like robustness with respect to samples, like if you perturb your samples a little bit, whether it's adversarial or it's just random, and you still have some robustness with respect to the input samples, that's quite interesting, right? Like yeah, and also like to continue on that, I've read some recent papers on continual learning that they're showing flat minima are going to be better for continual learning. And
Yeah,
when you're
I
yeah,
know.
right, so when you change the task, your loss landscape is completely changing, right? Like task 1 had a loss landscape, you had a flat region that you found, and then task 2 has potentially a very different loss landscape. And why is that still a good solution? I think like these are really interesting questions that one can think
Right.
about.
Yeah, the list of open questions can go forever, and I don't have answer to many of these because I think still for the SAM itself, let alone new applications like this kind of lifelong learning or things like
Right.
that. I still think there are things that I need to do in order to convince myself, or I think there are things that I can do that maybe can add a little bit more to the performance. So I'm mainly thinking about those things, but yeah, there are these new areas of more interpretable, more reproducible, and as you said, this lifelong learning. Yeah, these are all good problems. So I think regardless of what area in machine learning, you can find something about at the intersection of SAM and your area, and that makes an open problem for you.
Fantastic. Any more questions? Okay, if not, let's thank our speaker again. Thank you again for a wonderful talk, Hossein. This was really great.
Thank you so much. Thanks for having me. Okay, have a good day.
Have a good one. Bye.
Thank you. Bye.